So that's that. So first speaker for this session will be Alison, who's going to talk about starburst-driven winds.
All right. Thank you. I'm going to use this so I don't have to yell. I'm actually going to give two talks, 10 minutes each. So the first one is on extended starburst-driven winds and their connection to star formation history. So my collaborators and I have been studying for several years now these really interesting galaxies. So they're very compact, major mergers driving extreme starbursts, redshifts of around a half, driving these very fast winds. So they're really massive galaxies. Mass is around 10 to the 10.5 to 10 to the 11, and they're late-stage major mergers. These are HST images. So they're very compact. They have effective radii of only 100 parsecs. These are at redshifts of a half. These are the galaxies I was mentioning the other day. They do exist. They're just not that common. They don't have observed AGN in any wavelength, and we've looked at all the wavelengths, but they do have really concentrated starbursts. So approaching Eddington limited central starburst. So they have star formation rates of up to 200 solar masses per year or more, and star formation rate surface densities up to 2,000. Really, really extreme. So there's basically, these are stretched really hard to see the tidal features, but most of the light is in these very tiny central starbursts. And then they're driving outflows. This is magnesium 2 absorption from high res with velocities of 1,000 to 2,000 kilometers per second. So really fast outflows. So this is the first one that we looked at with KCWI. So most of the galaxy light, the starburst is in this tiny little circle here in the center. And then this is stretched real hard to see the tidal features. This is at redshift about a half. And then this is oxygen 2 emission extending 100 kiloparsecs end to end. So this is a bipolar outflow, so you mostly edge on. Looks sort of like the outflows you're familiar with, but just on scales much, much larger. It has a star formation rate of 150 solar masses per year. This is the largest isolated galactic outflow that's ever observed. So this is like the CGM information. Here's an outflow that's extending out into the CGM of this host galaxy. So the cool thing with KCWI is that we can not just get the morphology and extent, but the kinematics. So this is showing that same oxygen 2 nebula, and the color is the maximum blue shifted velocity, like how fast is the gas coming towards you. And so there's two color regions here. The lighter is slower outflow, and then the darker is a faster outflow. So these are showing spectra at different regions. So in the outer regions, the lighter colors here, there's just this single kinematic component, velocities of around 300 kilometers per second. As you go to these darker regions on smaller scales, there's two velocity components. There's this same one that you see further out, but then there's a broader blue shifted, faster outflow on smaller scales. So we think that there's two outflow episodes. If you look at the star formation history of this galaxy, doing SSP fits to the spectrum, you see that there were two recent starbursts. One within the last 7 million years and one about 0.4 gigayears ago. So the cool thing is if you take those numbers and match them back to the sizes and speeds of these two outflows, it all works out. So basically there's two outflow episodes. This larger, slower one happened first. If you take the size and speed and run it back, it matches with, sorry, I have those backwards. It matches with, oh no, that's right. The one that, the burst that was 400 million years ago, and then the smaller, faster one, you run it backwards, it matches that it happened at the time of the more recent burst. So the speeds and sizes of these two outflows in this galaxy are consistent with being driven by the two known starburst episodes. Okay, that was the first galaxy that we looked at with KCWI. Pretty spectacular. Then we went back to look at more. So this is a paper, it's not quite on AstroPH yet, but it's in the referee process, so it'll be there very soon. So we have 12 more galaxies with KCWI from this same parent sample. So here's Makani down here. These are all on the same scale. The tick mark is 20 kiloparsecs. So there's a handful that are also very extended, same as Makani. And then there's some that are more compact and round, but they're not really compact. They have radii of 20 kiloparsecs. And these nebulae trace outflows, so they have very high velocity dispersion. Again, they have multiple kinematic components. We're seeing multiple outflows, and they have very, very different kinematics than the stars, which we can also get from KCWI. For people who think about different emission lines, this is really neat. So this is comparing the oxygen 2 emission to the magnesium 2 emission. These galaxies have really strong magnesium 2 absorption from their winds, so there's not a lot of magnesium 2 emission, but there is some. It's weak. It's so weak that we can't fit it in every spectrum. So, in every spackle. So the color is showing you the magnesium 2 map stretched like really hard. So this is going out to like 1 sigma in magnesium 2. And then the white contours are the 4 sigma contours for oxygen 2. So the oxygen is more extended than the magnesium. And in particular, in the more extended sources, the oxygen 2 is much, much larger than the magnesium 2. There's just far greater signal-to-noise in the oxygen 2, and for these galaxies, it's a more useful tracer of the outflows because we can see it so far out. Okay, this is the main result from this paper, is that we find these trends between the star formation histories of these galaxies and the outflow extent and speeds that we observe. So we can take this sample of 13 galaxies and put it into 3 different categories. So here's an example of each galaxy in each of these categories. So the inset is showing you the velocity dispersion map. The blue is like 50 kilometers per second. The red is like 400 kilometers per second. And then this is showing the star formation history. So star formation rate, this is 0 to 1,000 as a function of look-back time in megayears. It's a log plot, so this is 10, then 100, and then 1 gigayear. So there's the galaxies fall into these 3 different categories. So the first is that galaxies with very high velocity dispersion at the center, that red light there, have the most recent star formation bursts. So you can see this really sharp rise in the last few million years, a very recent strong burst. So the gas at the center here that's moving very quickly is presumably a young outflow, while the larger scale outflow, and there's 2 kinematic components here, just like in Makani, is presumably an older outflow from an earlier burst. Then we see galaxies that they have high velocity dispersion at the center, higher than at the outskirts, but it's not quite so peaked. They have star formation histories that are also not so peaked. So there's a star formation burst that's recent, but it's not, you can see it's not that sharp of a rise like this one. So these galaxies, there's a handful of galaxies in each of these categories. These ones also have those 2 kinematic components, so we think there's 2 outflows here. And you're seeing the faster, younger one in the center, and then the slower, older one on the outskirts. And then we have a handful of galaxies, only a few, that have these really boring velocity dispersion maps. It's just low velocity dispersion all over. These have the oldest bursts of star formation, and they don't have a second kinematic component. It's just 1 outflow with low velocity dispersion, and they're pretty large. Okay, this is trying to quantify that a bit more. So this is comparing the outflow dynamical time to the light-weighted stellar age of the galaxy, so it's giving you information about the time since the burst. Most of the galaxies have 2 outflows, so this is kind of averaging over the 2. So each color here is a different galaxy. This is the 1-to-1 line between these. This is going from 0 to 50 million years. So this is the size of the outflow divided by the velocity times the light-weighted age. Basically, that's roughly the time since the burst. And generally, we were amazed that the galaxies fall so close to this 1-to-1 line. There are some large errors, and I get that it's not perfect, but this was pretty interesting to us. And we were finding that the outflows are populating and mixing with their CGM on timescales of less than 50 million years. And this general agreement here reinforces that these are starburst-driven outflows, and that the observed oxygen 2 is capturing the full extent of the outflow pretty well. You don't get this kind of agreement with magnesium 2. Okay, so the implication. So we found this clear connection between the star formation histories, and in particular, the sort of burstiness and the time since the burst, and the outflow episodes traced through their physical extent and the kinematics of the oxygen 2 gas. And most of the galaxies, the vast majority, have 2 outflows. So multiple outflow episodes are common. These are periodic outflows driven, we think, by different bursts of star formation. We can see multiple bursts of star formation in their star formation histories. These are not AGN driven. We don't see AGN in these galaxies. They're massive galaxies. They're going to have massive black holes, but we're not finding AGN at any wavelength. So we think that they are stellar driven, and given their star formation, and in particular their star formation rate surface densities, they're so extreme you can actually drive these outflows from stellar processes alone. In these very massive galaxies, where I think people tend to be a little like, oh, massive galaxy, AGN, low mass galaxy, stellar feedback. I'm just saying it's not quite that simple if you have a really extreme starburst. And these large-scale outflows are populating the circumgalactic media of these galaxies to radii of 20 or more kiloparsecs. So we're sort of seeing the CGM being replenished by these outflows. Okay, that was talk number one. I work on different fields, so here's an entirely different talk. This is a different paper. So switching to supermassive black holes and how they grow with cosmic time. We saw some of this on Monday. We'll see more of it on Friday. So just to remind you that AGN are important. So we've created an empirical model for supermassive black hole growth in different galaxy types. This is work with Brian Strazis and James Ayers. So we take the universe machine and we populate it with supermassive black holes following observations. So we start with the observed redshift 0 black hole mass stellar mass scaling relation. That's from observations from dynamical black hole masses, and we use separate observed relations for star-forming and quiescent galaxies. I'll show you the plots in a sec. I'm just talking through the methodology here. Then we start at redshift 0 with observation. Then we evolve back in time using the observed AGN, what's called specific accretion rate distribution function, which is basically the X-ray luminosity relative to the stellar mass of the galaxy for AGN for different galaxy populations based on stellar mass, redshift, and star formation rate out to redshift 2. And then we can see how the AGN scaling relation should evolve to redshift 2 and how much black hole growth there is in different galaxy phases since redshift 2. Okay, so that was words. Here's pictures. So we start with redshift 0, galaxy population, star formation rate, stellar mass. We divide it into 5 regions based on distance from the main sequence. So we've got starburst, main sequence, sub-main sequence, and then high and low quiescent. Then, this is again, so that's observational. Then we take universe machine. Then we put black holes into the galaxies in universe machine based on these scaling relations from redshift 0 of the black hole mass stellar mass. So this relation that we're using is these lines here. It comes from a paper by Jenny Green in 2020, which the title, it's like an annual reviews article on intermediate mass black holes, but hidden in the middle of it is this really nice update to the earlier observational work. And then the points here are a completely different paper, but showing something similar. So we take these scaling relations to put black hole masses into the galaxy's universe machine. Then we take these observed X-ray, basically luminosity distribution functions for galaxies of these different star formation types, stellar masses, and redshifts out to redshift 2, and then we can predict how galaxies move, individual galaxies move in this space with cosmic time from redshift 2 to redshift 0. Okay, so first result, how does the scaling relation evolve from redshift 0 to 2? So here's redshift 0, 0.5, 1, and 2. The lines here, again, are these observed redshift 0 relations. Those lines are the same, and all of these lines shows at that redshift our prediction. So the first thing you'll notice is that the difference between the quiescent star-forming population in this space is mostly erased by redshift even of a half, and it's even more gone at higher redshift. And then the relation flattens, the slope flattens at higher redshift, and matches at high redshift the normalization for the local quiescent population. Another way to think of this is there's a lack of low mass black holes at a given stellar mass at high redshift. And in fact, you see this pileup of like very low mass black holes. Basically, this is saying these black holes, all of their growth happened between these epochs and today. Okay, if we look at growth histories or evolutionary tracks of individual galaxies in this space, so this is the black hole mass versus the stellar mass, the points here with the symbol, the bigger points, are redshift 0. So if it's red, it's quiescent. If it's blue, it's star forming. If it's green, it's green valley at redshift 0. And then the lines show you going back to redshift 2, where the galaxy, how it evolved since redshift 2. Okay, so we see two, I don't want to like overstate this, but two general different pathways here. One that's more horizontal and one that's more vertical. So for galaxies that have high mass black holes at redshift 0 above 10 to the 8, they're basically almost horizontal tracks. It's a log plot, so there can be some growth, but it's very, very small in terms of the growth of the black hole. Meanwhile, the galaxy is still growing in stellar mass. For lower mass black holes, they've had a lot of relative growth since redshift 2. to redshift 0, and their stellar mass was more in place. So one takeaway here is that galaxies don't generally, we're not finding with this model that galaxies evolve along these redshift 0 scaling relations. It's more that they evolve towards the redshift 0 scaling relation, and they've either first run their black holes or their stellar mass relative to together, and then they catch up by redshift 0. So going back to these relatively horizontal tracks here, there's very little black hole growth since redshift 2 in the most massive black holes observed today. That means they formed the bulk of their mass before redshift 2. There has to be early buildup of the most massive black holes. So this implies a substantial population of overmassive black holes at high redshift, which we have been seeing exist. So that's great. It is really important to take into account the scatter in these redshift 0 scaling relations. So models or simulations that don't take into account that substantial scatter that is seen in observations at redshift 0 won't produce this diversity of growth pathways. So this is just for kicks. We were like, let's instead use Korman-Dean-Hoe. Instead of sigma, this is stellar mass. But basically, it's a tight relation, no dependence on star formation rate. And then what do we see in terms of growth histories? That's small, so I'm going to zoom in for you. So here's a zoomed in version. Basically, they're mostly horizontal. There's a little bit of growth this way, but it's mostly horizontal. So again, still not enough black hole growth to explain the most massive black holes. But we know that there's a lot more scatter than this at redshift 0 in this space, this black hole mass, stellar mass space. And a lot of papers are finding this dependence on star formation rate. So it's really important for modelers and simulators to take this into account. In terms of which galaxy phase is the black hole growth happening in, so this is showing the black hole growth that's cumulative since these redshifts for different galaxy types. So this is quiescent low, quiescent high is actually up here, starburst is here, and then main sequence and submain sequence is at the top. So basically, most of the black hole growth since redshift 2 is predominantly occurring in galaxies on the main sequence and below the main sequence, submain sequence. While the AGN fraction is higher in the submain sequence galaxies than on the main sequence, there's just more galaxies, therefore more AGN on the main sequence, and they spend more time there, so they cancel out. Starbursts, we were like, why are starbursts so low? They have AGN, and they have bright AGN, but it's a short-lived galaxy phase, so it doesn't lead to as much growth of the black hole by redshift 0. Okay, if I have a couple more minutes. So we tested a bunch of, we were really, I don't know, concerned, surprised at these horizontal tracks. And we were like, why are we not growing enough? Like, why are the massive black holes not growing? So we tested a bunch of different models. So our fiducial model, which is all the plots I've been showing you so far, there's no correlation between the ratio of the black hole mass to the stellar mass and the AGN accretion rate. We basically just allowed it to be kind of random, fitting the observations. But then we were finding there's not growth in the massive black holes. So we were like, okay, let's just artificially introduce a correlation in each of these galaxy populations between the AGN specific accretion rate and this ratio. So basically, the more overmassive the black hole relative to the galaxy, let's like just give it a higher accretion rate as long as it still fits the observations. And then just to like really push it, we have this ridiculous extreme model, which is not physical, where we're like, let's just put all the AGN in the most overmassive black holes, and that's the only place they exist, just to see what happens. And here's the difference in their growth histories. So this is what I was showing for the fiducial model. So these vertical paths go away, and this extreme model, of course, that's not going to happen. We put all the AGN in the most massive galaxies. But it doesn't really change anything for the massive black holes. So even if we do absurd things, we can't make those black holes grow since redshift 2. So all the high redshift JWST overmassive black hole people should be very happy right now. Good job. And then this is the evolution of the scaling relations. They're like identical. So the evolution that we're predicting in the scaling relations is very robust to which galaxies we put the AGN in, depending on their black hole properties. Okay, so last slide, the implications. So the black hole mass versus stellar mass scaling relation, we're saying that it should evolve to redshift 2. The slope should flatten. The difference between the starburst and quiescent galaxies, that normalization should go away by redshift of 0.5, and the normalization should match at high redshift what it is for quiescent galaxies at low redshift. There's also about 4 orders of magnitude total span or scatter in these observed relations at redshift 0. It's really important to include this scatter in models. Otherwise, you don't get this diversity of pathways to the redshift 0 scaling relations that are observed. So we're finding that most galaxies don't evolve along these relations, but rather towards them since redshift 2. And it's really hard to grow massive supermassive black holes since redshift 2. So this implies there must have been very substantial growth at earlier.
Did you take into account black hole growth from galaxy mergers? In other words, could you be more specific about the mechanism whereby the massive galaxies are growing as opposed to, you know, if it's mergers, then we all sort of expect that the black holes will merge too.
Yeah, so I'm trying to remember back several months ago when we had this conversation on our telecon about mergers. So we definitely are taking into account mergers. I don't think we were explicitly putting the AGN in the merging galaxies. I do feel like we tested this and we figured it can't be more than a factor of 2, so it just didn't seem, it's not going to fix the problem. But I can look back at exactly what we did, because we talked about this a lot and we did look into that, and we just thought it was not a big merger.
All right. So firstly, I have a short comment on Sandy's question. So I think, firstly, there's a significant delay between galaxy mergers and black hole mergers. So it is still kind of less clear. Well, yeah, it is true that for massive galaxies and massive black holes, this delay could be shorter because the dynamical frictions and other hardening mechanisms may speed up the process, but it's still quite indirect argument, and also people have different opinions about black hole merger rates that we can infer from, say, nanograph results, because people don't all agree that they exclusively come from, say, massive black holes below redshift 2. There are some exotic scenarios that people are still talking about. Secondly, a question. I really enjoy your second part of your talk. I have a question about the X-ray data that you used. So we know that galaxies and black holes, they presumably grow in mass over time, but practically when you are observing using those X-ray surveys, the lower limit in the observable galaxies increase their mass limits. I mean, towards higher redshifts, yeah, you can only see higher and higher mass galaxies. So these two things go the opposite directions, and how, I'm very curious how you map galaxies that are, for example, at redshift 0, there must be galaxies that just made it to your observable limits in galaxy mass, right? For example, 10 to the 9, well, for this sample, maybe 10 to the 10 solar mass. And at higher redshift, they must be lower mass, and they have already dropped out of your X-ray data. Then how do you do that?
Yeah, so I'm trying to remember whether we just used the limit at high redshift and only used that mass range across all redshifts. I think that is what we did. But you're right, you have to take into account that you can't see to lower stellar mass at high redshift. So that is in here, and I just can't remember how we solved it in the end, but I do think probably that we just cut the mass limit to be complete, but I can double check that. Yeah. And sorry, just to go back to a sec, the question about mergers, it's really interesting. There's two parts to this. One is, when do you trigger the AGN, and then when do the two black holes merge? Those are different timescales. So you could get substantial growth, maybe, from the AGN triggering phase before they've merged, but then you're only going to get a factor of 2 from the merger. That was the conclusion we came to in the end. So we're taking into account the AGN part when they're observed as AGN, but the merger itself, whenever it happens, is only going to be a factor of 2. Yeah. I don't think you're going to get a factor of 10. You need a factor of 10 to fix this. Yeah, they're really flat. Yeah.
Okay, one last quick question while James sets up.
Yeah, can you, regarding this very extended and high velocity outflows, can you exclude that those are due to an AGN which switched off? Because we know that AGNs are intermittent and
Yeah.
simulations show that the outflow cannot last the AGNs by several million years.
Yeah, so no, we can't exclude that there was some previous AGN event that we're not seeing now that drove these. But we don't have to invoke that. Like, we can explain it with what we do see, which is these extreme starbursts. They're really extreme. They're not just normal starburst galaxies. They're quite extreme. So, also we looked at things like, is there a correlation between the outflow velocity and the O3 luminosity? And the answer is no. And for AGN-driven outflows, there is. So we really don't think that these are AGN-driven. I think the AGN phase, it comes back to this other question, like when do you trigger the AGN versus when do you trigger the starburst? These seem to be starburst-driven, but they must have massive black holes.
Okay, let's thank